When a Linux system cannot mount a file system or suddenly refuses to write to storage, it can feel like the machine is rejecting you at the worst possible moment. A service that ran fine yesterday might now fail because its data directory is unavailable, or a reboot might leave you staring at errors about missing mounts that you have never noticed before. These problems are especially stressful because storage is a shared dependency for almost everything, so one mount failure can cascade into many other symptoms that look unrelated. The right response is not to panic or to start changing settings randomly, because mount problems are often solvable once you identify which layer is failing. A mount failure might be about discovery, such as the system not finding the device it expects, or it might be about trust, such as the system finding the device but refusing to mount it because it believes the file system is inconsistent. In this lesson, you will learn to separate the major categories and apply first response triage that stabilizes the system and protects data. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A clean mental model begins with what mounting actually means in Linux, because the word mount is more than a metaphor. In Linux, file systems are attached into one unified directory tree, which means storage devices and network shares become accessible at a specific location in that tree. The mount action is the moment where the operating system connects a file system to a mount point, and from then on, reads and writes go through that connection. Under the hood, Linux uses a layer called Virtual File System, VFS, to present a consistent interface to different file system types, which is why your programs can open files without caring whether the data lives on one disk, another disk, or a remote share. This also means that a failure can occur at different boundaries, such as failing to reach the underlying device, failing to interpret the file system, or failing to enforce access rules safely. When you understand mounting as a structured relationship between the tree, the file system, and the device, error messages stop feeling random and start pointing to specific parts of that relationship. The first category of failure is simply that the system cannot mount because it cannot find what it is supposed to mount. This can happen when a disk is missing, when a partition layout changed, when a device name changed, or when a removable or network resource is not present. Many Linux systems rely on persistent identifiers rather than unstable device names, such as identifiers stored in configuration that describe which file system should appear at which mount point. If that mapping is wrong, the mount attempt fails even if the disk is healthy, because the system is looking in the wrong place. A beginner mistake is to assume that if a mount fails, the file system must be corrupted, but discovery failures are often just mismatches between expectation and reality. The triage question is whether the system sees the storage at all, because if discovery is broken, repair needs to focus on identification and availability rather than on file system integrity. This is also why mount failures often show up right after hardware changes, cloning, or updates that change how storage is enumerated. A second category is when the system finds the device but cannot mount because the file system metadata does not make sense or cannot be trusted. File systems keep structural information that tells the operating system how to locate directories, files, and free space, and if that structure is inconsistent, mounting can be refused to prevent further damage. This can occur after unsafe shutdowns, after storage errors, or after corruption that changes critical metadata. Many modern file systems include journaling or similar techniques that help maintain consistency, but journaling is not a guarantee that everything will always mount, especially if there are underlying read errors or the damage is severe. From a first response perspective, the key is to treat this as an integrity problem, which means your priority shifts toward protecting the remaining data and avoiding actions that worsen the inconsistency. Beginners sometimes keep retrying mounts in the hope it will work, but repeated attempts do not repair structure and can add stress if the underlying hardware is unstable. A safer mindset is to recognize that refusal to mount is often a protective behavior, not an arbitrary denial. A third category, and one of the most confusing for beginners, is when a file system mounts but becomes read-only, even though you did not ask for it to be read-only. This behavior often surprises people because the system still looks mostly functional and reads still work, so you may not notice until something tries to write. The reason this happens is that file systems often have safety mechanisms where, if the kernel detects serious errors while writing or updating metadata, it remounts the file system as read-only to prevent further corruption. In other words, read-only can be a defensive move made by the operating system when it believes continuing to write would cause more damage. This is why a sudden read-only state is not just an inconvenience. It is a strong signal that something went wrong in the storage path, such as a file system error, a hardware I/O failure, or a loss of consistency that was detected during normal operation. The most important beginner lesson is to interpret read-only as a symptom that demands investigation, not as a setting you can simply toggle away without consequences. When you encounter a read-only file system, it helps to think about what the system is trying to protect. A file system is not just data blocks. It is also the structure that maps names to blocks, tracks free space, and enforces the rules that keep files from overlapping. If that structure becomes unreliable, continued writing can turn a limited problem into a widespread one. So Linux may choose to freeze writes rather than risk silent damage. This is also why services behave strangely when storage becomes read-only, because many services do small writes constantly, such as updating lock files, tracking offsets, recording state, and writing logs. A beginner might chase each service error independently, but the underlying cause is often the shared inability to write. The right triage move is to confirm whether the issue is localized to one mount point or affects multiple, because one read-only mount can be isolated, while multiple read-only mounts might indicate deeper storage subsystem instability. In either case, the calm approach is to preserve the system state and avoid aggressive write activity until you understand why the system lost confidence. Another puzzling scenario is when the file system is mounted read-write in concept, but a specific partition, directory, or application path still cannot be written to, leading to messages that imply permission or policy issues. This is where you must separate file system writability from access control writability. A file system can be healthy and writable, yet a user or service might lack permission due to ownership, mode bits, access control list, ACL, entries, or other policy mechanisms. Conversely, permissions can look fine, but writes can still fail if the file system is effectively read-only due to mount options or error state. Beginners often toggle between blaming permissions and blaming disks, but a more mature approach is to classify the problem as either systemic, where all writes fail on that mount, or scoped, where only some users or paths fail. Scoped failures point toward access controls and application expectations, while systemic failures point toward mount state, file system integrity, or hardware. This classification step is fast and prevents wasted time because it tells you whether to think like a security boundary problem or a storage boundary problem. Mount options are another conceptual layer that can make a partition appear unwritable even when the device and file system are fine. A file system can be mounted with options that explicitly enforce read-only behavior, either because the configuration requested it or because the system chose it during boot due to detected risk. This can happen intentionally, such as mounting certain media read-only to prevent tampering, or unintentionally, such as a mistaken configuration change that set a mount to read-only. It can also happen when the system decides a safe mode is necessary after detecting inconsistencies, in which case the mount options reflect a defensive posture. The important idea is that the mount is a contract between the kernel and the file system driver about what operations are allowed, and options are part of that contract. Beginners sometimes think of mount options as a minor detail, but in operations they can explain why a partition behaves differently than expected even when everything else appears normal. A careful responder treats mount options as evidence about intent and safety, not as arbitrary toggles. Failures to mount can also be influenced by ordering and dependency issues during boot, which is why mount problems often appear to start suddenly after a reboot. Many services assume certain mount points exist, and if those mount points are not available when the service starts, the service may fail and then keep failing even after the mount becomes available later. Similarly, if a mount depends on network availability or on another file system being present, timing changes can cause a mount to fail early even though it would succeed later. This is not about typing commands. It is about understanding that boot is a sequence and mounting is part of that sequence. For Linux Plus level reasoning, the key is to think about whether the mount failure is consistent across time or whether it is a race between when the mount is attempted and when the resource becomes available. If it is a timing issue, the storage might be fine, and the fix is about dependency alignment rather than about repair. If it is consistent, the issue is more likely identification, integrity, or access control. Network-based mounts add another dimension to the problem, because a mount can fail even when local disks are healthy, simply because the remote endpoint is unreachable or slow. From the perspective of the local system, the symptom might look like any other mount failure, but the cause is now tied to network conditions, name resolution, authentication, or remote service availability. This is why a COM triage approach asks whether the problematic mount is local or remote, because remote mounts have an additional dependency chain that includes network health. Even without getting tool-specific, you can reason about this by observing whether local storage paths work normally while the failing mount corresponds to a remote share. Beginners sometimes assume the local machine is broken when the real issue is that the remote resource is down or that a connectivity policy changed. This is another example of why mount failures are often about relationships between systems, not just about disks. When you treat mounts as dependencies, you learn to isolate whether the failure lives on the local host, the network path, or the remote service. Write failures also have a special relationship with free space and resource limits, because a file system can be mounted and healthy, yet still refuse writes when it runs out of space or runs out of nodes. The result can look like a permission problem, because applications often report generic write failures when they cannot create files. This is why disk-full puzzles and mount-write puzzles overlap. A mount might be present, but the file system can still be at a constraint boundary that prevents new data. The important mental move is to avoid assuming that a write failure must be a permissions issue just because it mentions access denied or cannot write, because applications do not always distinguish between policy denial and resource exhaustion in their error reporting. The triage skill is to consider whether writes fail everywhere on that mount, whether the failure began after a period of growth, and whether system behavior suggests that temporary files and logs also cannot be written. When you think in these terms, you can avoid chasing the wrong layer and instead address the constraint that is actually blocking progress. Hardware and media reliability issues can also manifest as mount failures and read-only behavior, and this is where symptoms can become especially confusing. A disk that is beginning to fail may sometimes read successfully and sometimes return errors, which can cause mounts to fail intermittently or to succeed and then later remount read-only when a write error occurs. This intermittent behavior is emotionally hard for beginners because it destroys the expectation of consistent cause and effect, but it follows a predictable pattern when you view it as degraded reliability rather than as random chaos. The practical lesson is that intermittent mount or write problems should increase suspicion of the storage path, including the device, its controller, and the cables or virtualization layer that presents it. When the underlying reads and writes are unreliable, higher-level layers cannot guarantee integrity, so defensive behavior like read-only remounting becomes more likely. A mature triage approach treats this as a data protection scenario, where preserving what is still readable becomes a priority. Even in a learning context, this reinforces the principle that availability and integrity are connected. When integrity is threatened, systems often sacrifice write availability to prevent worse outcomes. Another important conceptual distinction is between failures caused by misconfiguration and failures caused by genuine corruption, because the recovery thinking differs. Misconfiguration means the system is being told to do the wrong thing, such as mounting the wrong identifier at the wrong mount point, applying the wrong mount options, or expecting a file system type that does not match what is actually present. In these cases, the data can be intact, and the fix is about aligning configuration with reality. Corruption means the data structures are actually inconsistent or unreadable, and the fix often requires careful repair strategies that prioritize preserving data. Beginners sometimes confuse these because both can produce similar surface messages, but the timeline often helps. If a failure began immediately after a configuration change, misconfiguration rises in likelihood. If it began after crashes, power loss, or hardware warnings, corruption rises in likelihood. The reason this matters is that misconfiguration fixes are usually low risk and reversible, while corruption-oriented actions can be more invasive and must be handled cautiously. Good triage protects you from making corruption worse when the real issue was simply a mismatch. A calm first response process for mount and write failures is built on narrowing scope, identifying the stage, and protecting data while you learn. You begin by determining whether the mount is missing entirely, present but read-only, or present and read-write, but selectively unwritable for certain users or paths. You then consider whether the resource is local or remote, whether the issue is consistent or intermittent, and whether the timing relates to a reboot or a recent change. You treat read-only remounting as a strong integrity signal, not as a nuisance, and you avoid actions that generate heavy writes when integrity is in doubt. You also remember that many downstream service failures are consequences of storage unavailability, so you focus on restoring stable storage first rather than chasing secondary symptoms. This way of thinking mirrors other Linux Plus troubleshooting topics. Classify the layer, isolate the scope, and choose the least risky next step. When you apply it here, mount problems stop being mysterious because you have a framework that turns messy symptoms into a clear decision tree in your head. As we conclude, it helps to summarize the three main puzzles in a way that reinforces the operational mindset rather than encouraging memorization. A mount that will not mount is often a discovery or integrity problem, meaning the system either cannot find the expected device or cannot trust the file system structures enough to attach them safely. A file system that becomes read-only unexpectedly is frequently the kernel protecting the system after serious errors, which signals that continuing to write could increase corruption and that investigation should focus on integrity and the storage path. A partition that appears mounted but is not writable can be caused by mount options, resource exhaustion, or access controls such as ACL behavior, and the key skill is distinguishing systemic unwritability from scoped unwritability. Across all cases, first response triage is about reading the stage of failure, narrowing scope, correlating with recent changes, and protecting data by avoiding risky actions until you understand the category. When you can do that calmly, you turn storage failures from crisis moments into structured troubleshooting problems, which is exactly the kind of reliability Thinking Linux Plus is trying to build in you.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.